All right, everybody, ladies and gentlemen, welcome to Chem 241's final lecture. Monday's review day, but today's our final new stuff, and I've cut it way down. It could be a lot more, and it's not going to be because we're all stressed to the max. And here we go. Now, sharing screen. Up here, there's an announcement, very important. I've decided that you are only responsible for all things epoxide from chapter 11. So if it has anything to do with epoxides, that's the stuff. Why? Epoxides are very useful. We use them in synthesis on each exam in 242. So the very last thing today, we're going to show how they react, and that you're looking ahead. Okay, a few more announcements about the final, because I know. Okay, fine. Tried to grab everything. Move it down. There's a sample final study guide, section 8 at Moodle. And I got my hand on the screen here. Study guide, very detailed. I am also going to post answers for the multiple choice, even though you'll see on the study guide, it says you guys are responsible for this on your own. No, I'm going to do it for you. I've done it. I just got to find the document and post it for you. So key soon. Hey, it's okay. Study without the key. That's not bad, right? Check your work later. Okay, section 8 Moodle. And I want you to read that before you ask any questions about the final. And here's a layout of the sections. So right now we're going to be talking about mechanisms to make epoxides. I got some marks from my shirt here. I forgot this is a shirt that can write on a screen, you know. Watch this. Yeah. No, wrong. Okay, never mind. I had an idea. And we're going to do a review mechanism because this guy here, halohydrin. So you could look up in the index of the textbook on how to make halohydrins, and you'll see that this is a review mechanism. The water reacts with the bromine because the bromine was stored in water from the beginning. And it's been reacted sitting in the bottle in the back room a long time ago. There's bromine with a leaving group on it. We can say these words now. We didn't use those words before. And pi bond attacks it. Leaving group does what leaving groups do. It leaves. Lone pair comes back to which carbon? Say it again. More substituted carbon. That's something we used to say every day for a long time, right? It's been a while, but we're back. Triangle time. Real triangle. That means bonds everywhere. Isopropyl, and we got a bromine. Bromine switch color to black. We'll put it on a dash. If one bond's on a dash, the other bond's on a dash. Physically impossible to have one be a wedge and one a dash when you're in a triangle. And the other product is water. Although, you know, there's water from before. It's the solvent. But you can use the water you just made to do a backside attack on which carbon? More substituted carbon. That's that one. Then you get an oxonium. Oxonium intermediates are very common in organic chemistry, aren't they? So we have on a wedge the new water with 2 H's on it and a plus. That's an oxonium. And the old dash on the left did not break. And what's the last step? Yeah, getting rid of the proton off the oxonium using the solvent because there's more solvent than anything, and the pKb is the best compared to Br minus. It's an old discussion. That's why I went so fast. There you go. Water neutralizes. This next reaction is not a new reaction either. What's going on? OH minus is becoming H2O. What kind of reactions is that are right away? Acid base. So that's my base. Where's my acid? Tertiary alcohol is my acid. I'm drawing the H here and scribbling off the old one because I have to show the bond breaking. I didn't change the molecule. I just drew the bond. Lone pair, grab H. Sigma become lone pair. Trying to get rid of this red mark here with, no, it's too big. Bothering me. Yeah, what can you do? Okay. Hey, if I wrote this on the screen here, could you finish the mechanism for me? I got a nucleophile. It's a strong nucleophile this time. You don't usually see those inside the molecule. And a carbon next door with a leaving group. Backside attack. Leaving group leaves. End of story. Arrows are SN2 arrows, although you couldn't call this an SN2. There's only one molecule, right? But that is a backside attack. In your mind, you call it SN2. Backside of a dash is a wedge. Hey, the new bond's a wedge. Right? No. You made an epoxide. These are both the same epoxide. So if you had to summarize what makes something an epoxide, what would you say? It is a specific version of a more general function group. What functional group has carbon, then oxygen, then carbon, and neither one of those carbons is a carbonyl? Ether, yes. Chapter 11 is ethers. Epoxides are a type of ether, and they're in a very small ring. Epoxides are in ring size 3. So the epoxide part is this part. Cyclic ethers that are in a triangle. How's that for an answer? That covers it. Cyclic ether in a triangle answers the question, what is an epoxide? So we used an old mechanism, and then we did an acid base, and then we did an NGP with our conjugate base. We got an epoxide. The bottom one, we're using a new functional group. If I had to ask you what functional group that you already know this one's closest to, what would your guess be for this guy right here? It's a carboxylic acid and a peroxide. Both of you had it. You got the combination. So it's a, we're gonna portmanteau it, gluing two words together and make a new word. It's a peracid. Generic carboxylic peracid is, hello? Hi. RCO3H. And yes, it has a peroxide in the acid. That's why I got the per. And guys, this is it's not the easiest mechanism, but it's close. It's 4 arrows and that's it. No intermediates. Peracids are very reactive. They're a little on the dangerous side. This one in particular is pretty dangerous. If you need to use peracetic acid, which this one is, you got to follow the recipe for making peracetic acid and then use it within minutes, or else you might have an explosion on your hand. Many peroxides are explosive. Okay? So, you ready? The driving force here is to get rid of the OO bond. Because why? No, anytime you have an atom with lone pairs bonded to another atom with lone pairs, That is the most reactive feature of the molecule. It's called lone pair repulsion. So you're going to pop it open with the alkene. Check these arrows out. You don't see attacking of oxygen too often. But the fact is, when you attack that oxygen, you can resonate in here. And you can resonate out here. And get a lone pair there. Now, this mechanism doesn't sit well with me when I see arrows coming towards arrows, because that's not natural, is it? Arrows don't like arrows. But if you remember, there was a sequence here. Then that first arrow is done, and the fourth arrow is later. So if you number your arrows, you don't have to. First arrow is that one. Second arrow is this little guy over here. Third arrow's here. So the fourth arrow doesn't know the first arrow happened. It's not like it says, I'm going to go towards those electrons, because electrons wouldn't do that. Electrons don't go towards electrons. You're right. My second one is a lone pair onto O. I'm sorry, what was your question? You're right. Yeah, my arrow numbers are badly done. Somebody's paying attention to the order I did them. 2 was this one, the resonance. Thank you. 3 was this one, which is really, it's resonance and then acid base, isn't it? And 4 was the last guy there. Sorry about that. Numbers were wrong. Now they match the textbook. So the secret, guys, you're going to have to remember which O to attack. Because if you get that wrong, the mechanism won't work. So describe to me which of the oxygens got attacked by the pi electrons in the alkene. Good. The O with an H. Yeah. I like to look for excuses to use the biology words distal and proximal. You'll see me do it in lab a lot. I do it in lecture too. So in terms of the carbonyl, didn't I attack the distal oxygen, the one that's further from the carbonyl? But if you like her way of remembering better, I think hers is more direct. Just attack the O that has the H. Okay? Don't attack any other O. And then break the OO, and it becomes a carbonyl, right? And you're curious what it looks like? I think on your final, in fact, I know on your final, I also give you the side product. Hello? All right. I give you the side product, and it looks like this. Right there. Isn't that the result of what would happen down here? You get a carbonyl right there. The old single double bond to O is now a single bond to O, and the O picked up a proton. And I made a mistake with arrow 4 anyway. I'm having one of those days, ladies and gentlemen. Yeah. You know what this would give? Wouldn't give an epoxide. There'd be a cation up here. Or here. I don't like it. So fix arrow 4 for me. I'm going to do my best to just grab arrow 4. It thinks they're all together. Oh, that's really sad. 1 and 2 are cool. Where did arrow 3 go? To the H from the pi, right? And I labeled it with a 3. It gets labeled. 4 goes, comes back to the carbon that's a better carbocation. Which carbon is that? Yeah, I just want to give the same answer 3 times on the same quiz. Which carbon do I come back to with this pair of electrons? The more substituted carbon. That's great. We get to do it one final time this semester. Is that 4 all by itself? Yeah. Here, I'm going to move the 4 because I can. I moved the 4 down here. That did not go as smoothly as I wanted, but 4 arrows. Attack the distal O first, resonate into the carbonyl. Old carbonyl protonates. There you go. Then you get an epoxide. So it looks like same starting material gives the same result. Why do we need two methods? Good question. Why do we ever need two methods? One, the first method doesn't always work. So we need another method. Two, money. The per acid, and safety too. The per acids can either be dangerous or expensive. The simple ones are dangerous and the more complicated ones are more expensive, but they're safer. There you go. This is dirt cheap up here, but messy. Nobody likes using bromine in the lab, trust me. It's filthy, nasty. Don't like it. That's why we like lecture course. You don't get messy. All right, next up, we're going to be talking about naming of epoxide. So we'll come back to that one. And see you soon.